In our last video, we took a look at the particle in a box wave function and its properties associated with probability density. We looked at normalization and we looked at the probability within particular regions inside the box. In this video, we're going to take a look at some of the other properties that the wave function allows us to determine about the particle in a box. So we'll start by looking at just the general nature, reviewing the general nature of eigenvalue equations. And then we'll look at how this applies to the wave functions associated with the particle in a box. And then finally we'll calculate expectation values for some of these properties within the box, and we'll show how that's done. So starting with basics of eigenvalue equations. We know from our earlier discussions of the postulates of quantum mechanics that for every observable, that is every measurement we can make in the lab, there's a corresponding mathematical operator for that particular observable. And we also know that what that means is that we will take this operator and we'll operate on the wave function representing the state of our system. Now, the question is, if we operate on our wave function and we get a constant represented here by the letter lowercase o times our original function, we have an eigenfunction. So that's a real question, first of all, is our wave function an eigenfunction of a particular operator? So if it is, if we do find out that by operating on the wave function, and we've looked at some examples of this in past videos, and we get a constant times the original function, then if we get that situation, as noted, O is the eigenvalue, and that means that if we go into the lab and make a measurement on an eigenfunction, that eigenvalue is what we expect as the result or outcome of that measurement. And it will be the only possible outcome of measurements. So if we have an eigenvalue equation, then we know the eigenvalue is the only possible result of those measurements. Now, if it's not an eigenvalue equation, if we don't get a constant times the original function, and we'll look at a specific example of that in a few minutes, then we know we have to deal with what are we going to get in the lab? How do we know what we're going to get in the lab? Is there a way to do that? And we'll be dealing with that a little bit in this video, and then in the next video after this we'll talk about how we can make that determination. All right, so here's a table from your text that shows the operators for various different kinds of observables that we see. The first one here being the momentum operator, which we've already looked at. It may look a little bit different than what I have posted in some of the other videos because we have this negative IH bar. Well, that negative IH bar is the same thing as H bar of I. I tend to favor that form because I don't have to remember to write a negative sign when I use H bar over I. You should be able to prove to yourself that these two are equal to each other. So that's our momentum operator. We also have a kinetic energy operator here in the second one listed that is also sometimes listed as T with a little caret over it. Is sometimes the symbol that's given for the kinetic energy operator. We'll note that kinetic energy operator is equal to the momentum operator squared over 2m, just as kinetic energy in the classical system is equal to the momentum squared over 2m. And you'll notice that if there's a classical equation that we can translate that into the quantum mechanical operator by using the appropriate operator substitution in those equations. Potential energy, again, we'll note that sometimes that's represented by V with a little caret over it, so the V hat is sometimes used as that. And the Hamiltonian operator, again, as we noted before, is just the total energy operator, and that's the sum of the kinetic energy operator and the potential energy operator. Angular momentum operators are listed here. I won't talk about those now. And you may ask, well, in chemistry, are we actually going to be dealing with angular momentum? The answer is yes. These operators are actually very, very important when we talk about electronic behavior in atomic and molecular systems. So we'll be coming back to that in future videos. All right, so let's talk about momentum, and specifically momentum associated with the particle in a box. Question is, if we have a particle in a box, what happens when we measure the momentum in the laboratory? So we're going to take our operator for momentum, okay, and we're going to operate on our function. And there's our particle in a box wave function. So we're taking a derivative, and when we take that derivative, we'll note that we get this cosine function here on the right. Okay, so question, is it an eigenfunction? Answer, well, no, because we're starting out with a sine function and we're ending up with a cosine function. So we do not have a constant times the original function. The function has changed. So here's a circumstance where our wave function is not an eigenfunction, the momentum operator. And what does that mean? Well, it means that if we go into the lab and measure the momentum of a particle represented by the one-dimensional box wave function, we're going to get more than one result. All right? If it's an eigenfunction, there's only one possible outcome. If it's not an eigenfunction, there are multiple outcomes, and we have to deal with that. All right? So, how do we deal with that? Well, typically in the lab, when you have multiple measurements, what do? You calculate the average value from those multiple measurements. So, that's where expectation values come into play. We're going to use the expectation value to calculate an average of our measurements. Now, we have yet to say what those possible measurements might be. That will be in the next video, but at this point we're just going to look at the average measurement. So we use the formula for expectation value. And here's our general formula that we introduced in an earlier video when we talked about the postulates of quantum mechanics. The average value is equal to this integral where we are taking the operator operating on our wave function integrated over all space to determine that average value. Alright, so the average momentum in a particle in a box, how do we set that up? You can use MathCAD to do this. You can also do it with Wolfram Alpha, and I'm going to leave that for you to do. Just provide you with a few details here as you go through this calculation. So if we want to calculate the average momentum, we have to use the momentum operator. We're operating on our 1D box wave function. And in this case, all space, since a particle cannot exist outside the box, all space is just from 0 to A, the boundaries of the box itself. So we don't have to go from negative infinity to infinity, just remembering that the particle only exists within the box. So we're going to take our momentum operator, which remember is, of course, equal to h bar over I. So this just becomes, h bar over I d by dx that part of the integral just becomes h bar over I times the derivative of psi with respect to x. So on the previous slide, we showed that the derivative was a cosine function. So we're going to substitute that into our integral, and we're going to do the integration. And as I said, you can do this in MathCAD. You can use Wolfram Alpha to do it. And you should be able to show, when you do this, that the average momentum is equal to 0. Okay? All right, well, so does that make sense? Would be one of the questions we would ask. The average momentum equal to 0. Later on in the next video, when we look at how we can determine what the individual outcomes might be, we'll see how this can easily be the case. But if you think about a particle going back and forth between the walls of a box, just kind of draw it here, all right? Half the time it's moving in, say, a plus x direction, and half the time it's moving in a minus x direction. Well, remembering, of course, that momentum is a vector quantity, that means that half the time it can be moving with a momentum of plus mvx, and half the time it can be moving with a momentum minus mvx, and of course the average of those two is going to give us a value of 0. So the expectation value for momentum being 0 is actually consistent with what we might predict based on classical behavior. And again, we'll take a look at this in more detail from a quantum mechanical perspective in our next video. All right, so now let's talk about position. All right, we just asked the question, what is the average momentum? Let's ask about average position. You should be able to prove to yourself, based on the position operator, which is just multiplication by x, you should be able to show to yourself that under these circumstances that operating on psi is not going to give us a constant times the original function because, of course, x is not a constant. It's a variable. So x operating, the position operator operating on psi gives us x times psi, and therefore it is not an eigenfunction, and we're going to end up with multiple values, which once again means that we have to deal with expectation values. All right, so that means this is the integral we're going to have to evaluate. Now, x being just multiplication, we can rearrange this a little bit, so we end up with the integral of x times psi star psi, which if we have a real function is just x times psi squared. And so for the particle in a box wave function, this is the integral that we'll need to evaluate to determine the average position. Okay. Now, I'm actually going to carry this one out. I actually did carry this one out using Wolfram alpha. If you type this particular line into Wolfram alpha, int Wolfram alpha will interpret as meaning integrate. And so here's x, and here's our wave function here. So we're going to integrate x times the square root of 2 over a. There's our normalization constant times the sine function squared. So we're going to integrate that from 0 to a. Again, 0 to a represents all space for the particle in a box. And we end up with a result from Wolfram alpha. And again, I just pasted this directly from Wolfram alpha. We get this long equation here, which has sine terms and cosine terms in it, and it has n. So this is a general equation that will work for any n value, any quantum number value. And you might say, okay, we got this nice little equation, but we can simplify this. And again, I'm going to leave this to you, because if you consider the fact that n is a whole number or natural number, we'll be able to eliminate some terms in this particular expression and simplify it greatly. So this is what I want you to do. I want you to go through this equation and assume that n is a natural number and eliminate terms in that equation and come up with a much simpler form. And then ask yourself if it makes sense. Actually, if you've done this correctly, it should in fact make sense to you. In fact, let me just ask you this right now, something to consider. If you have this particle within this box with two walls, and I was to ask you, okay, I'm making the measurement of the position of the particle in the box, and I'm making a bunch of these measurements, and as the particle in the classical world is moving back and forth between the walls, and I take all these positions and I average them together, what do you think that's going to be equal to? And does this quantum mechanical result match what you might think it would be equal to? And again, I'm going to leave it to you because I'm asking you to simplify this on the worksheet that accompanies this video. So think about that. Again, the key is this issue, n is a natural number. If you use that and look at this particular equation, you should be able to simplify it a great deal. Okay, so this ends our video on expectation values and the one-dimensional particle in the box. In our next video, we'll talk about superpositions and how the superpositions will allow us to determine not just the average expectation value, but actually the range of possible outcomes that we might expect from our measurements in the laboratory. So that's something that we're all going to look forward to enthusiastically. So stay tuned for our next video.